Hello everyone, I'm Professor Chia-Po Wei. I will post course information such as exam results or the solution of weekly quiz on the announcement board of Cyber University and on our course website. We will still use remote teaching and remember that the weekly quiz starts from Monday 8:30 a.m. and feel free to contact me or contact the teaching assistants if you have any questions about the course contents. In this week, we are going to learn sections 5.1 and 5.4. In section 5.1, we introduce the scalar product or the inner product in Rn. While in section 5.4, we introduce the inner product for more general vector spaces, such as polynomials, continuous functions, or matrices. Our textbook uses the scalar product to refer to the inner product in Rn. Recall that in Chapter 3, the vector space involves with two operations, the vector addition and the scalar multiplication. In Chapter 5, we will introduce another operation, that is the inner product operation. This operation enables us to define the angle between two vectors. And with the introduction of inner product, we are able to determine whether two vectors are perpendicular or not. Next, we introduce the scalar product in Rn. Let x and y be two vectors in Rn. Then x transpose y is called the scalar product of x and y. The scalar product is a scalar because x transpose y equals x1 y1 plus x2 y2 plus up to xn yn. Note that x transpose y equals y transpose x because the result does not change if we exchange x and y. Thus, the scalar product is commutative. That is, the order of x and y is not important. Given a vector x in Rn, its Euclidean length can be defined by the scalar product. That is the square root of x transpose x. We will use this symbol to denote the Euclidean length of x. The Euclidean length of x is also called the two-norm of x. Note that the two-norm of x is always greater than or equal to 0 because x transpose x is always greater than or equal to 0. Also note that the two-norm of x equals the two-norm of negative x because the negative one cancel each other out in the scalar product. Next, we define the distance between two vectors. Let x and y be vectors in Rn. Then the distance between x and y is defined to be the number, the two-norm of x minus y. We use the figure in this slide to visualize the distance between two vectors. Let x and y be two vectors in Rn. Then y minus x is also a vector in Rn. The distance between x and y is the two-norm of y minus x, which equals the two-norm of x minus y. In this slide, we introduce Theorem 5.1.1. if x and y are two non-zero vectors in R2 or R3, and theta is the angle between them, then x transpose y equals the 2 norm of x times the 2 norm of y times cosine theta. In view of Theorem 5.1.1, we are able to define the angle between two vectors in terms of the scalar product. That is, cosine theta equals x transpose y divided by the 2 norm of x times the 2 norm of y. To prove Theorem 5.1.1, consider the right-hand side figure. Let x and y be two non-zero vectors in R2 or R3, and theta is the angle between them. Then y minus x is also a vector in R2 or R3. By the law of cosines, we have the square of the 2 norm of x minus y equals the right-hand side. After some arrangements, we have the 2 norm of x times the 2 norm of y times cosine theta equals 1/2 times parentheses the square of the 2 norm of x plus the square of the 2 norm of y minus the square of the 2 norm of x minus y. By definition of the Euclidean length, the square of the 2 norm of x minus y equals x minus y transpose times x minus y. After expansion, we have the following four terms, and x transpose x cancels the first term in the outer parentheses, and y transpose y cancels the second term in the outer parentheses, and the minus sign cancels the minus sign. Thus, inside the parentheses, we have y transpose x plus x transpose y. Because the two terms are equal, so inside the parentheses, the result is 2 times x transpose y. After multiply with 1/2, we obtain x transpose y. And thus, the 2 norm of x times the 2 norm of y times cosine theta equals x transpose y, and the proof of Theorem 5.1.1 is finished. Below, we illustrate the physical meaning of inner product. Let x be the displacement of an object, and y denotes the force. Then the work done on that object equals the magnitude of force times the shift along the direction of force. The magnitude of force is the 2 norm of y, while the shift along the direction of force is the 2 norm of x times cosine theta. We can visualize the 2 norm of x times cosine theta by the left-hand side figure. By Theorem 5.1.1, we know the work done on that object equals x transpose y. That is, the work done on that object equals the scalar product of the displacement and the force. In view of Theorem 5.1.1, cosine theta can be expressed as x transpose y divided by the 2 norm of x times the 2 norm of y. If we define u as x divided by the 2 norm of x, and define v as y divided by the 2 norm of y, then cosine theta can be written as u transpose v. That is, cosine theta is the scalar product of u and v, where u is the unit vector along the x direction, and the v is the unit vector along the y direction. Next, we introduce Corollary 5.1.2, the well-known Cauchy-Schwarz inequality. If x and y are two vectors in R2 or R3, then the absolute value of x transpose y is less than or equal to the 2 norm of x times the 2 norm of y. The equality holds if and only if either x or y is the zero vector, or x can be expressed as lambda y for some scalar lambda. First, we discuss the inequality of 2. From Theorem 5.1.1, we know x transpose y equals the 2 norm of x times the 2 norm of y times cosine theta. Because the maximal value of cosine theta is 1, and the minimal value of cosine theta is negative 1, and thus the absolute value of x transpose y is always less than or equal to the 2 norm of x times the 2 norm of y. Next, we consider the equality of 2. If either x or y is the zero vector, then both sides of 2 are 0, and hence the equality always holds. If both x and y are non-zero vectors, then the equality of 2 holds if and only if cosine theta is 1 or negative 1. In this case, this would imply the two vectors are in the same direction or in opposite directions. And in this case, x can be written as lambda y for some scalar lambda. And the proof is finished. Next, we discuss the geometrical meaning of the inner product. Let x and y be two vectors in Rn, and the theta is the angle between the two vectors. And let P be the projection of x onto y. We know that if theta is less than 90 degrees, then P and y are in the same direction. If theta is larger than 90 degrees, then P and y will be in the opposite directions. Next, we define the scalar projection of x onto y, which is alpha. Alpha equals the 2 norm of x times cosine theta. If theta is less than 90 degrees, then alpha equals the length of P. If theta is larger than 90 degrees, then alpha equals negative 1 times the length of P. If we multiply both the numerator and the denominator with the 2 norm of y, then the numerator becomes x transpose y due to Theorem 5.1.1, and thus alpha equals x transpose y divided by the 2 norm of y. Next, we define the vector projection of x onto y, which is P. P equals alpha times u, and u is the unit vector along the y direction. So u is y divided by the 2 norm of y. And we substitute alpha with x transpose y divided by the 2 norm of y. and know that the square of the two norm of y equals y transpose y. Hence, P equals x transpose y divided by y transpose y times y. Finally, know that x minus p is orthogonal to p. That is, x minus p and p are perpendicular. Because P is an orthogonal projection of x onto y. In this slide, we discuss the equation of a plane in R3. Two vectors u and v are said to be orthogonal if u transpose v equals 0. That is, if the scalar product of u and v is 0, then the two vectors are orthogonal. We use the notation u perp v to denote the two vectors are orthogonal. The symbol perp means perpendicular, and we use the notation p1, p2 to denote the vector from point p1 to point p2. Let pi be a plane in R3, and p0 is a point in the plane, and n is the normal vector of the plane. Then any point in the plane pi must satisfy the following property. That is, P0P is orthogonal to the normal vector n. Or we can say the scalar product of P0P and the normal vector equals 0. Plane pi is the set of points P such that P0P is orthogonal to n. If we denote n as ABC and P0 as x0, y0, z0, then P0P is x minus x0, y minus y0, z minus z0. And because P0P is orthogonal to the normal vector, so we have the following equality. This equality holds for all points P in the plane pi, and this equality is the equation for the plane pi in R3. In example 8, we compute the distance from a point V to a given plane. The equation of the given plane is x plus 2y plus 2z equals 0. From the plane equation, we know the normal vector is equals 1, 2, 2. Our goal is to compute distance d from the vector v to the plane. And we can visualize the distance d in the bottom figure of this slide. The distance d actually is the length of P. P is the projection of V onto the normal vector n, and the distance from V to the plane equals the length of P. And the length of P is the absolute value of the scalar projection of V onto n. From the result in the previous slides, we know the scalar projection equals this term, and hence the absolute value of the scalar projection of V onto n equals the absolute value of the scalar product V transpose n divided by the two norm of n, which equals 2/3. In this slide, we discuss exercise 14. Let x1, x2, and x3 be vectors in R3. If x1 is orthogonal to x2 and x2 is orthogonal to x3, can we say x1 is orthogonal to x3? You can try to figure out the answer to this question and check whether your answer is correct or not. The answer to this question can be found in the last page of the slides. We have finished section 5.1 and we will introduce section 5.4, inner product space. The scalar product in Rn is introduced in section 5.1, and the scalar product in Rn can be generalized to the concept of inner product on any vector space, such as polynomials, continuous functions, or matrices. We can regard inner product as an operation. This operation has two inputs, that is, vectors x and y from the same vector space, and the output of this operation is a real number. If this operation satisfies the following three properties, then we say this operation is an inner product on vector space V. The first property says that the inner product of x and itself is greater than or equal to 0. The equality holds if and only if x is the zero vector. The second property says that the inner product of x and y equals the inner product of y and x for all x and y in the vector space. The second property means that the inner product is commutative. That is, the order of x and y is not important. The third property says that this equality holds for all x, y, z in the vector space and all scalars alpha and beta. The third property means that the inner product is linear in its first argument. That is, the inner product satisfies the homogeneity property and the additivity property in its first argument. A vector space V with an inner product is called an inner product space. We know that a vector space need not to have an inner product. Therefore, inner product space is a subset of the vector space. The definition of inner product is kind of abstraction. This kind of abstraction captures the essential properties of the inner product operation. The abstraction provides us a uniform interface to deal with the inner product in different vector spaces, such as polynomials, continuous functions, or matrices. In this section, we introduced two subsets of vector spaces. The first subset is the inner product space. The second subset is the normed linear space, which will be discussed later. The inner product space is a subset of the vector space because a vector space does not require to define an inner product operation. Similarly, a vector space does not require to define a norm operation, and therefore the normed linear space is a subset of the vector space. We will show that every inner product can induce a norm, but not every norm can be induced by an inner product, and therefore inner product space is a subset of the norm linear space. Our textbook does not have this figure, and this figure is introduced here for your information. We will introduce different examples of inner product spaces. The first example is the vector space Rn. In Rn, the standard inner product is given by x transpose y, which is the scalar product of x and y. The definition of inner product is not unique. We can define another inner product as the summation of xi, yi times wi. We can regard wi as the weight of xi, yi. If we set wi as 1 for I from 1 to up to n, then the second inner product reduces to the standard inner product. You can verify by yourself that either the standard inner product or the second inner product satisfies the three properties in the definition of the inner product. Any operation can be an inner product as long as it satisfies the three properties in the definition of inner product. Next, we consider the second example, the vector space of Rm times n. The vector space of matrices of dimension m times n. For this vector space, we usually define the inner product as the summation of aij times bij, where the index I begins from 1 up to m, and the index j begins from 1 up to n. Aij is the ij entry of matrix A, and the bij is the ij entry of matrix B. You can verify by yourself that this definition of inner product indeed satisfies the three properties in the definition of inner product. The third example is the vector space Pn, the polynomials of degree less than n. For this vector space, we define the inner product to be the summation of p of xi times q of xi, where the index I begins from 1 up to n, and the p, q are polynomials of degree less than n, and the xi, x1, x2 up to xn are given and distinct real numbers. We will verify that this operation satisfies the three properties in the definition of inner product. First, we verify that this operation is commutative. That is, the result does not change if the order of p and q is changed, which is true because p of xi times q of xi equals q of xi times p of xi. Next, we verify that this operation satisfies the third property. That is, this operation is linear in its first argument, which means this operation satisfies the homogeneity and the additivity property in its first argument, which is straightforward. You can check this by yourself. In view of the above, we know the second and the third properties are in the definition of inner product are satisfied. Next, we prove the operation satisfies the first property. That is, the inner product of P and itself is greater than or equal to 0. And the equality holds if and only if P is the zero polynomial. To see this, know that the inner product of P and itself equals the summation of P of xi times P of xi, which is the square of P of xi, and is equal to and is greater than or equal to 0. The equality holds means each term in the summation must equal 0. Therefore, we have P of xi equals 0 for I from 1, 2 up to n. Recall that x1, x2 up to xn are distinct real numbers, and this means P has n distinct roots, which is a contradiction because P is a polynomial in Pn, and each polynomial in Pn is of degree less than n. So the degree of P is less than or equal to n minus 1, and P cannot have n distinct roots unless P is the zero polynomial. Hence, the equality holds if and only if P is the zero polynomial, and therefore the proof is finished. The fourth example considers the vector space of continuous functions defined on the interval AB. For this vector space, the inner product is usually defined by the integration of f of x times g of x from a to b, where f and g are continuous functions defined on the interval AB. We will verify that this operation satisfies the three properties in the definition of the inner product. First, we verify that this operation is commutative. That is, the result does not change if the order of f and g is changed. This operation is commutative because f of x times g of x equals g of x times f of x. Next, we verify that this operation satisfies the third property. That is, this operation is linear in its first argument. That means this operation satisfies homogeneity and additivity property in its first argument, which is straightforward. You can check this by yourself. In view of the above, the third and the second properties in the definition of inner product are satisfied. Next, we prove the operation satisfies the first property. That is, the inner product of f and itself is greater than or equal to 0. And the equality holds if and only if f is the zero function on AB, or equivalently, f of x must be identically 0 in the interval AB. If f of x is not identically 0 in AB, this means there exists some x0 in AB such that f of x0 is not 0. Because the square of f of x is continuous, there exists a subinterval I of AB containing x0 such that the square of f of x is greater than or equal to the square of f of x0. divided by 2 for all x belonging to the interval. We can visualize these conditions by the lower right figure. Because the square of f of x is a continuous function, so we can find a subinterval I containing x0 such that the square of f of x is greater than or equal to the square of f of x0 divided by 2 for all x belonging to the subinterval I. Then we use p to represent the length of interval I. Then we have the following condition: the inner product of f and itself is the integration of the square of f from a to b, which is greater than or equal to the integration of the square of f of x over interval I. The inequality holds because the interval I is a subset of AB. Then we have the integration over interval I is greater than or equal to the square of f of x0 times p divided by 2, which is greater than 0. Because f of x0 is not 0 and p is positive, we have proved that if there exists x0 in AB such that f of x0 is not 0, then the inner product of f and itself is greater than 0. Hence, if the inner product of f and itself equals 0, then f of x must be identically 0 in the interval AB. If this is not the case, there will exist x0 in AB such that f of x0 is not 0, and this will imply the inner product of f and itself is greater than 0. In view of the above, the proof is finished. In this slide, we discuss basic properties of inner product spaces. If V is a vector in an inner product space, then the length or the norm of V is given by the square root of the inner product of V and itself. We use the notation the norm of V to denote the square root of the inner product of V and itself. We know that the norm of V is always greater than or equal to 0, because due to the first property in the definition of inner product, the inner product of V and itself is always greater than or equal to 0. Two vectors u and v are said to be orthogonal if the inner product of u and v equals 0, and we use the notation u perp v to denote u and v are orthogonal. Here the symbol perp means perpendicular. Theorem 5.4.1 is the well-known Pythagorean Law. If u and v are orthogonal vectors in an inner product space V, then the square of the norm of u plus v equals the square of the norm of u plus the square of the norm of v. This equality can be visualized by the right-hand side figure. The three norms corresponds to the three edges in the right-hand side triangle. and the norm of u plus v is the longest side of the triangle. We are already familiar with the Pythagorean law in R3, and in fact, the Pythagorean law can be generalized in arbitrary inner product space. Next, we prove the Pythagorean law. The square of the norm of u plus v equals the inner product of u plus v and itself. Then, because the inner product is linear in its first argument, so we have the second equality. And because the inner product is commutative, so we have the third equality. And again, because the inner product is linear in its first argument, and we have the fourth equality. And since the inner product of u and v equals the inner product of v and u, and hence we have the fifth equality. And we know u and v are orthogonal vectors, and therefore the inner product of u and v equals 0. Hence, we have the last equality, and therefore the square of the norm of u plus v equals the square of the norm of u plus the square of the norm of v, and the proof is finished. In this slide, we discuss example 1. Consider the vector space of continuous functions defined on the interval between -1 and 1. The inner product is defined by the integration of f of x times g of x from -1 to 1. And our goal is to compute the norm of 1 and the norm of x and the norm of 1 plus x. The norm of 1 equals the square root of the inner product of 1 and itself. The inner product of 1 and itself is 2, and therefore the norm of 1 is the square root of 2. The norm of x equals the square root of the inner product of x and itself. And the inner product of x and itself equals 2/3, and therefore the norm of x equals the square root of 6 divided by 3. We know that 1 and x are orthogonal because the inner product of 1 and x equals 0. Then we can use the Pythagorean theorem to compute the norm of 1 plus x. The square of the norm of 1 plus x equals the square of the norm of 1 plus the square of the norm of x. And after some computation, we obtain the square of the norm of 1 plus x is equals 8/3. We can verify our result by directly compute the square of the norm of 1 plus x, which is the inner product of 1 plus x and itself. And the result is also consistent with the result obtained by the Pythagorean law. In example 2, we consider the vector space of continuous functions defined on the interval between -pi and pi. And we use a constant weight function, the inverse of pi, to define an inner product. The inner product equals the inverse of pi times the integration of f of x times g of x from negative pi to pi. With this inner product, we can compute the inner product of cosine x and sine x, which equals 0. And this means cosine x and sine x are orthogonal. Next, we compute the inner product of cosine x and itself, which equals 1. And this means the norm of cosine x equals 1. And thus, cosine x is an unit vector because its length is 1. Next, we compute the inner product of sine x and itself, which also equals 1. And this means the norm of sine x is 1. And so sine x is also an unit vector because the norm of sine x equals 1. Therefore, we say cosine x and sine x are orthogonal unit vectors. Because cosine x and sine x are orthogonal, we can apply the Pythagorean law to compute the square of the norm of cosine x plus sine x, which equals 1 plus 1. So the square of the norm of cosine x plus sine x equals 2. This type of inner product plays a key role in Fourier analysis applications. If U and V are vectors in an inner product space, and the V is not the zero vector, then we can define the scalar projection of U onto V and the vector projection of U onto V. We have already seen similar definitions in section 5.1. The difference is that here we replace the scalar product with the inner product. And the scalar projection of U onto V is alpha, which equals the inner product of U and V divided by the norm of V. And the vector projection of U onto V is P, which equals alpha times the unit vector along the V direction, which equals the inner product of U and V divided by the inner product of V and itself times V. You can refer to section 5.1 to more detailed explanation. In this slide, we prove two observations. If U is not the zero vector and P is the vector projection of U onto V, then we have the following two observations. Observation A, U minus P and P are orthogonal. And observation B, U equals P if and only if U is a scalar multiple of V. And the two observations can be visualized by the figure in the previous slide. From this figure, if P is the projection of U onto V, then U minus P will be orthogonal to P. And we know if U equals P, then this means U and V are in the same direction. First, we prove observation A. Then we compute the inner product of U minus P and P, which equals the inner product of U and P minus the inner product of P and itself. After some computations, we know the inner product of P and itself equals alpha squared, and the inner product of U and P also equals alpha squared. Therefore, the inner product of U minus P and P equals alpha squared minus alpha squared, which equals 0, and hence U minus P and P are orthogonal. Next, we prove observation B. First, we prove the if part. If U is a scalar multiple of V, we want to show U equals P. And because P is the vector projection, so P equals the inner product of U and V divided by the inner product of V and itself times V. Then we substitute U with beta V. After some computations, we know P equals beta V, which equals U, and therefore we have shown P equals U. Next, we prove the other direction. We prove the only if part. For the only if part, suppose U equals P, and our goal is to show U is a scalar multiple of V. If U equals P, then U equals alpha times the unit vector along the V direction. Then know that alpha divided by the norm of V is a scalar, and therefore U is a scalar multiple of V. And our proof is finished. In section 5.1, we have proved the Cauchy-Schwarz inequality in R2 or R3. And in this section, we will prove the Cauchy-Schwarz inequality for any inner product space, which is the theorem 5.4.2. If U and V are any two vectors in an inner product space V, then the absolute value of the inner product of U and V is less than or equal to the norm of U times the norm of V. The equality holds if and only if U and V are linearly dependent. To prove this theorem, consider the inner product of U minus lambda V and itself. And this inner product is greater than or equal to 0 for any scalar lambda. This is due to the first property of the inner product. After some arrangements, we have the square of the norm of U minus 2 lambda times the inner product of U and V plus lambda squared times the square of the norm of V. Then we define C as the square of the norm of U, and define B as -2 times the inner product of U and V, and define A as the square of the norm of V. Then the above inequality becomes C plus B lambda plus A lambda squared is greater than or equal to 0. By completing the square, we obtain the right-hand side inequality. This inequality must be held for all real number lambda, and therefore the numerator must be less than or equal to 0. Otherwise, there will exist some real number lambda such that this inequality fails to hold. So we have b squared minus 4 times AC is less than or equal to 0. Then we substitute the definitions of A, B, C into this inequality and obtain 4 times the square of the inner product of u and v minus 4 times the square of the norm of u times the square of the norm of v is less than or equal to 0, which leads to the absolute value of the inner product of u and v is less than or equal to the norm of u times the norm of v. And last, we consider the equality holds. The equality holds when if and only if u minus lambda v equals the zero vector. This is due to the first property of the inner product. Then we have u equals lambda v, which means u is a scalar multiple of v, and this means u and v are linearly dependent. And the proof is finished. If u and v are non-zero vectors, then by the Cauchy-Schwarz inequality, we know the inner product of u and v divided by the norm of u times the norm of v. This ratio is between -1 and 1. So there exists a unique angle theta in the interval between 0 and pi, such that cosine theta equals the ratio. This means we can use the inner product to define the angle between two non-zero vectors. And in the right hand side is an example, and this example illustrates how to find the angle between two vectors. Consider the vector space of continuous functions defined on the interval between 0 and 1. And the inner product is defined to be the integration of f of x times g of x from 0 to 1. And our goal is to find the angle theta between 1 and x. And to this end, we need to compute this ratio. So first, we compute the inner product of 1 and x, which equals 1/2. And next, we compute the square of the norm of 1, which equals 1. And we compute the square of the norm of x, which equals 1/3. And therefore, cosine theta equals the inner product of 1 and x divided by the norm of 1 times the norm of x, which equals the square root of 3 divided by 2, and the theta equals pi divided by 6, which is the angle between 1 and x. In the previous slides, we have shown that an inner product can be used to define a norm, but not every norm can be induced by an inner product. In fact, the word norm in mathematics has its own meaning that is independent of an inner product. That is, the norm does not require to be related to an inner product. Below is the definition of the norm. A vector space V is said to be a normed linear space if for each V in the vector space there is associated a real number, the norm of V, satisfying the following three operations. Satisfying the following three properties. If the operation satisfies the following three properties, then we say this operation is the norm for the vector space. The first property is that the norm of V is greater than or equal to 0, and the equality holds if and only if V is the zero vector. The second property is that the norm of alpha v equals the absolute value of alpha times the norm of v for any scalar alpha. The third property is that the norm of u plus w is less than or equal to the norm of v plus the norm of w for any vw in V. And the physical meaning of the norm is the length of a vector. And therefore, the first property is intuitive because the length of a vector is always greater than or equal to 0. And the length of a vector equals 0 if and only if the vector is the 0 vector. And the length of alpha v always equals the absolute value of alpha times the length of a vector. And the third property is the well-known triangle inequality. Consider the right-hand side figure, where the three edges are the three norms, the norm of v plus w, the norm of v, and the norm of w. The triangle inequality says that the sum of any two edges is greater than or equal to the remaining edge. In this slide, we prove that the operation defined by the square root of the inner product of V and itself defines a norm on the vector space. And we need to verify the three properties in the definition of the normed linear space. First, we verify the norm of V is greater or equal to 0, and the equality holds if and only if V equals the 0 vector. By definition, the norm of V equals the square root of the inner product of V and itself, which is greater than or equal to 0, and the equality holds if and only if V is the 0 vector. The above is true because due to the first property of the definition of inner product. Next, we verify the second property in the definition of the normed linear space. The norm of alpha v equals the square root of the inner product of alpha v and itself. After some computations, this term becomes the square root of alpha squared times the inner product of v and itself, which equals the absolute value of alpha times the norm of v, and hence the second property is satisfied. Next, we prove the triangle inequality. The square of the norm of u plus v equals the inner product of u plus v and itself. After expansion, we have three terms, and by the Cauchy-Schwarz inequality, the inner product of uv is less than the norm of u times the norm of v. Hence, we have this inequality. Then, by completing the square, we have the square of the norm of u plus the norm of v. Hence, the norm of u plus v is less than or equal to the norm of u plus the norm of v, and hence the triangle inequality is satisfied, and the proof is finished. In this slide, we show that it is possible to define many different norms on a vector space. We define the p norm as the right-hand side for any real number p greater than or equal to 1. That is, the p norm defines a norm for any real number that is greater than or equal to 1. The p norm satisfies the three properties in the definition of normed linear space. Note that if p is less than 1, then this definition will violate the triangle inequality, and hence if p is less than 1, then this definition does not define a norm. Below are two special cases. The first special case is p equals 1. Then the one norm is the summation of the absolute value of xi. If p equals 2, the two norm is the square root of the summation of the square of xi, which is the square root of the inner product of x and itself. Another important norm is the uniform norm or infinity norm. The infinity norm equals the max of the absolute value of xi for I from 1 to up to n. In example 5, given a vector x in R3, we compute the one norm, the two norm, and the infinity norm of x. Note that when p equals 2, the two norm is derived from the inner product. However, if p does not equal 2, then the p norm does not correspond to any inner product. And therefore, if p is not equal to, then the p norm will not satisfy the Pythagorean law. In the next example, it can be verified that x1 and x2 are orthogonal. That is, the inner product of x1 and x2 is 0. And it can be verified that the Pythagorean law is satisfied for the two norm. However, for the infinity norm, the Pythagorean law is violated because the square of the infinity norm of x1 plus the square of the infinity norm of x2 equals 20. However, the square of the infinity norm of x1 plus x2 equals 16. Next, we discuss exercise 30. And in this exercise, we need to sketch the set of points in R2 such that one of the following conditions is satisfied. In condition A, the one norm of x equals 1 corresponds to the equation the absolute value of x1 plus the absolute value of x2 equals 1. The set of points in R2 satisfying this equation is the diamond shape. Next, we consider the two norm of x equals 1, which corresponds to the equation the square of x1 plus the square of x2 equals 1, which is the equation for a circle. Thus, the set of points in R2 satisfying this equation is a circle. Next, we consider the third condition, the infinity norm of x equals 1, which corresponds to the max of the absolute value of x1 and the absolute value of x2 equals 1. And the set of all points in R2 satisfying this equation correspond to a square in R2. Recall that in the vector space Rm times n, we can define an inner product by the summation of Aij, Bij, and we can use the inner product to define the Frobenius norm, which is the square root of the inner product of A and itself. You can verify that the Frobenius norm satisfies the three properties in the definition of the normed linear space. In example 3, we show how to compute the inner product and the Frobenius norm of matrices of dimension 3 times 2. We have finished sections 5.1 and 5.4, and I have selected some exercises for you to practice. The answers of the selected exercises can be found at the end of the textbook and in the next slide. In sections 5.1 and 5.4, we have learned the definition of the inner product and the many related examples. Inner product enables us to define the angle between two vectors. And we also learned the definition of the norm. The physical meaning of the norm is the length of a vector. I hope you can understand the physical meaning behind the definitions of inner product space and the normed linear space. Feel free to leave comments about this video or the slides, and don't hesitate to ask if you have any questions.